Alright, so we're going to check 12 and 13 today. Obviously 12 is really short. It just kind of follows up. Chapter 11 we did sampling. So with that sampling, you do certain types of studies sometimes, so I felt it was important to mention. Because there's not much in chapter 12 that we go over, but I felt like these 3 points were worth hitting at least once. Observation studies. In observational studies, researchers don't assign choices, they simply observe them. The example I have for it, a study took a random sample of adults and asked them about their bedtime habits. The data showed that people who drank a cup of tea before bedtime were more likely to go to sleep earlier than those who didn't drink tea. So they didn't force anybody to drink tea or not to drink tea. They just observed their bedtime habits and noticed that, hey, 22 people drank tea, and those people seem to go to bed earlier than the ones that don't. Observational study. A retrospective study versus a prospective study. So in a retrospective study, first you identify the subjects and then collect data on their past. A prospective study, you identify subjects in advance and collect data as it unfolds. So my sister does biostatistics at MUSC. A lot of times they have to do retrospective studies. Because if you want information on people that have heart disease, and you want to know what led to them getting heart disease, if there was any underlying factors, a lot of times what you do is you find people with heart disease and ask them, well, what did you do in your 20s, 30s, 40s, and kind of take note of those factors, right? If you had to do a prospective study of that, you would have to select a random assortment of, say, 100 people, track them their entire lives, kind of hope that a few wind up with heart disease, so you'll have all that information, right? But most of them might not. So you wind up spending a whole bunch of your resources on a bunch of people that's not even going to add to your data set. You see what I'm saying? So you have to follow, say, 100 people, maybe 88 of them don't even wind up with heart disease. So you've wasted 88 people worth of resources for 50 years. It's a lot to go into. So a lot of times people will do retrospective studies. All right, chapter 13. So we'll get back into doing some numbers now. But first we're going to talk about probability, kind of get a sense of what it is. So, from randomness to probability. In a situation in which we know what possible outcomes occur, but we don't know which particular outcome will happen, that is random phenomenon. So, we know what could happen. Maybe it's flipping a coin. We know we can get a heads or a tails, but when we flip a particular coin, we don't know if we're going to get a heads or a tails. Does that make sense? So, we know the possible outcomes, but we don't know the exact outcome until we actually do the flip in this case. So flipping a coin, we have 2 possible outcomes, either a head or a tails. We're not going to consider that it can land on its side. But we don't know which particular outcome will happen. If we don't know the coin is a fair coin, we can determine the percent of times we expect a heads outcome by doing an experiment. We'll flip the coin and then record the outcome. Okay? So that's what we'll do. That's our simple experiment there. We know we can get a heads or tail, don't know which one we're going to get. Determine which one we're going to get, we flip it. Easy enough? First heads, or first flip, we get a heads. So if we're trying to figure out the probability of getting a heads, and all we can base it on is this experiment with the coin, and we only flip it 1 time, and we get a heads, right now we see that there's a 100% chance of getting a heads based on that 1 flip. Does that make sense? If I flip it again, and I get another heads, it's still a 100% chance that I get a heads. Make sense? If I do a 3rd flip, and I get a tails, now there's a 66.6% chance that I get a heads. Does that make sense? How that's working? And I can keep going and going and going. As you continue to go, this percent gets closer and closer to the true percent. Does that make sense? So the more experiments we do, the closer we get to the overall percent. So if it's a fair coin, eventually it should get really, really close to 50-50. Okay. All right. That's all that says. In general, each occasion upon which we observe a random phenomenon is called a trial. At each trial, we note the value of the random phenomenon and call it the trial's outcome. When we combine our outcomes, we call it an event. We call the collection of all possible outcomes the sample space. The sample space for our coin example would be simply the sample space that equals heads and tails. Our 2 possible outcomes. We get a head, we get a tail. We're flipping 2 coins at the same time, our sample space changes. I can get a head on the first coins and a head on the second coins. I get a head on the first coin, a tail on the second coin. I get a tail and then a head, or a tail and a tail. Does that make sense? Flipping 2 coins. So I've got these different combinations that I can get from my sample space. Now, if the order of the coins matter, they're equally likely. I can get this 25% of the time, this, and this all 25% of the time. If the order doesn't matter, then I can get this 25% of the time. If the order doesn't matter, those are the same, right? Then that will happen 50% of the time. Does that make sense? And the other one happens 25. Now, we've got this law here called the law of large numbers. It says that as we repeat a random process over and over, the proportion of times that an event occurs does settle down to a number. We call this the probability of the event. Okay? So, if I keep doing this experiment over and over and over and over and over again, once I've done it a whole bunch of times, it should settle down to pretty close to a number. Hopefully 50-50 and it'll be a fair point. Does that make sense? That's the law of large numbers. It does require two key assumptions. The random phenomenon must not change. The outcomes must have the same probabilities for each trial. And the events must be independent. The outcome of one trial doesn't affect the outcome of others. What that means, or what that doesn't mean. So, let's see here. So if I don't know, I'll use my favorite examples. Okay, we got a football game that we don't get to play this year, right? Yeah. If Vegas says that Clemson has a 70% chance of winning and a 30% chance of winning, right? Year to year. Overall, the overall proportions of Clemson beating Carolina 70-30, right? Nothing else matters. We're just looking at that percent. So I would assume this year that Clemson would have a 70% chance of winning, right? The likelihood of them winning the next year would still be 70%, would still be 70% after that. Does that make sense? Or if you want to go even more simple to these flipping coins, if you got a head, and it's a 50% chance you get a head on each one, and a 50% chance you get a tail on each one, right? So when I flip it one time and I get a head, that doesn't change the percent. If it changes the percent, we can't use the law of large numbers. If for some reason I flip a head and somehow the coin knows that it's gotten a head and it won't get a head next time, and there's a 25% chance the next time instead of a 50% chance, which would be really, really weird to have a coin that did that. But if that was the case, then we couldn't use law of large numbers because the percents are changing. The percents need to stay constant. Typically with this, the only times you see the percents changing are in cases of like non-replacement. So if I had like a bag of marbles, I had red marbles and blue marbles, and I had 20 red marbles and 20 blue marbles. In my first draw, I pull out a marble, I have a 1 out of 40 chance or whatever of getting a marble, and then I've got a 1 out of 20 chance of getting a red, a 1 out of 20 chance of getting a blue. If I don't put that marble back, my next draw, say it was a red, I only have a 19 out of 20 chance of getting, does that make sense? A 19 out of 40 chance of getting an actual red marble, because that one doesn't have as many to choose from. We'll get into that a little bit more later. So they need to be independent. The first one can't affect the second one. The probabilities can't change. Most of that holds for the ones we do this semester. Just need to keep that in the back of your mind. Empirical probability is based on the observation of an event's outcome. So probability of a heads is 50%. That's your empirical probability. So we've noticed that this coin, after we did a whole bunch of trials, it turned out the heads happen about 50% of the time, tail happens about 50% of the time. That would be your empirical probability for that event. Okay. What a lot of people run into is they like to use what is generally called the law of averages that doesn't mathematically hold. What the law of averages states, quote unquote, is that, okay, I'll give you an example. If I flip a fair coin, so it's 50-50 heads, tails, I get tails 235 times in a row. Okay? 236th time, I feel like I really got to get a heads if it's truly a fair coin because it's more likely. Is that really true? No, because the coin doesn't know that it flipped a tail 235 times in a row. The coin's an inanimate object. Does that make sense? So you're just as likely on that 236th flip to get a tail as you were on that 235th. Does that make sense? Now that run seems highly unlikely, and it usually is, but it can happen. There's a small probability of it happening, right? So the law of averages doesn't hold. It's like people go to Vegas, I don't know, maybe they're doing the roulette wheel or whatever, and they vote, or they put big money on red like 5 times in a row and lost 5 times. Like, oh, it's got to show up red this time. Well, the roulette wheel doesn't know it rolled red 6 times in a row, or at least it's not supposed to. In Vegas, it might, right? But like I said, the table doesn't know what it's done. If it's truly the equal part, it's not going to make a difference. Does that make sense? You're just as likely that roll as you were the roll before it when you lost. So it doesn't make it more likely you'll win the next time. That's where people get in trouble with the law of averages. Okay. Modeling probability. When the probability comes from a mathematical model and not from an observation, it's called theoretical probability. Think of a card game. We can model a card game with 52 cards and find the likelihood of each outcome of draws. In order to do so, we'll take the number of draws or the number of outcome of desired draws and divide it by the overall possible draws. So if I wanted to know the probability that I draw a 5 out of a deck of cards, how many 5s do I have in the deck? 4, right? I got 4 suits and each of them have a 5. So there's 4 opportunities to pull a 5. There's 52 cards to pull from. Probability of pulling a 5 is 4 out of 52. Not rocket science, right? It's pretty easy. Okay. So, all you really need to know is your sample space, which in this case is 52 cards, and the counting can seem kind of easy. But for certain examples, it can get really, really difficult. So if we look at the coin flipping example. So if you flip a coin twice, your sample space is heads, 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 tails, tails, heads, tails, tails, right? That seems simple. You only got 4 opportunities to choose from. But if you flip a coin 100 times and you want to see what's the probability of getting exactly 67 heads, then your first thing in your sample set will be 100 heads. Your next one will be 100 heads and 99 tails, with your 99th tail being your last one. Your next one will be 99 tails, with your 99th tail being, let's illustrate. That's hard to conceptualize. So my sample space is just basically going to be really, really long, right? So I got 100 of these in my sample set. And I got the one with tails. And I got all these heads. But then I have a tails and then a heads. And then I got to do every other combination of heads and tails that there could possibly be 100 times. Does that make sense? That's a lot to write down. You're not going to be able to do it, right? So while counting may seem easy with small examples, that's not basically the best approach. Does that make sense? And we'll find in chapter 16 a mathematical way to do it with your calculator that'll make it really, really easy. Okay. The other thing I have to mention is personal probability. We use the language probability in everyday speech all the time to express a degree of uncertainty without basing it on long-run relative frequencies or mathematical models. We call this subjunctive or personal probability. Although personal probabilities may be based on experience, they're not based on either long-run relative frequencies or equally likely events. They don't display the kind of consistency that we need to have, that we'll need the probabilities to have. Personal probabilities would be like if I went out and I was shooting basketball, I set up for a free throw, and I said, I feel like I got a 90% chance of making this free throw. I didn't go out and do an experiment, stand on the line, shoot 10 free throws and make 9 and use that as my percent. I just felt like that's the chance I had when I was shooting that time. It's a personal probability. That's kind of the example I use for that. I've got fill in the blanks here because y'all need to fill in some blanks. We'll leave this for y'all. All this information is above. Okay, so y'all did kind of roll a little bit on that. Some of y'all, I don't know, I haven't got this class working yet, but I'm still grading your quiz. Trust me, y'all could use some matching stuff in practice. We'll leave that for you. If you need to, if you come back next class and couldn't figure one out, let me know. I'll let you know what it is. But y'all could use a little go back and review the notes practice from what I saw on that last one. So I'll have that back on Tuesday. We'll go over it on Tuesday. Okay. It wasn't terrible, but it wasn't perfect either. So a lot of y'all did really good. Some of y'all looks like you're struggling a little bit. I know definitions are tough though. So rule number 1: perform probability. If the probability is 0, the event never occurs. Likewise, if the probability is 1, the event always occurs. Probability can never be negative. No matter how unlikely an event is to occur, probability can never be greater than 1, unless you're Dabo Sweeney, no matter how likely the event is to happen. Okay, right? So you really can't give 110%. You can only give 100. Fair enough. But your probabilities are going to range between 0 and 1. If the probability is 0, then you know the event never happens. Ever, right? If it happens and you get a 1, that means the event always happens. Right? Okay. If the random phenomenon only has one possible outcome, it's not very interesting or random. If you know what happens all the time, it's not random. It's always going to happen. So we need to distribute the probabilities among all the possible outcomes a trial can have. When we assign probabilities, we need to be sure that we distribute all the available probability. The probability of the entire sample space has to be 1. So that's just what that says underneath it right there. The set of all possible outcomes of the trial must have a probability of 1. If you took 104 here, at least think they still do some 104. We stopped doing issues, I think. If you've looked at sets before, right? It's kind of like Venn diagrams. Okay. This is your sample space. I'm just using this to illustrate. Okay. You've got an event A that happens, right? Event A happens, but these are all the events in this space that could happen. So the event A plus the event B plus the event C, all that space has to be filled. Does that make sense? You can't have, okay, the probability of A is 25%, probability of B is 20%, probability of C is 20%, and that's all I can get. No, it's not. You've got leftover probability. That makes sense. You only got, what, 65%. You still got another 35% that you got to account for. Does that make sense? So all your options have to be listed in your sample space. Okay. Rule number 3. Set of outcomes that are not in event A is called the complement of A. So the complement rule is pretty important. It's going to save you a lot of time and make calculations a lot easier on several examples. Same thing. You got your sample space here. You got your event A here, right? So all this says is the probability of an event not occurring is 1 minus the probability it does occur. So if the probability that A happens is 30%, so this circle takes up 30% of your sample space, what's the probability A doesn't happen? 70, right? It's whatever's left over. So you'll have 70% left out here. So A complement is 70%. That's all we let that stand for. A to the C stands for A complement. Does that make sense? Okay. All right. Disjoint are mutually exclusive. Events have no outcome in common. The addition rule says that you can add the probabilities of the events of disjoint. Two disjoint events A and B. The probability that one or the other occurs is the sum of the probability of the two events. Probability of A or B equals probability of A plus the probability of B. Right they are disjoint. Disjoint. You got event A, you got event B. They can't happen at the same time. Does that make sense? So you can't flip a heads on one flip and have also flipped the tails on that same flip. Does that make sense? Disjoint. Now if they're not disjoint, they kind of look like a Venn diagram. A and B intersect. Does that make sense? That means they have something in common. They can happen at the same time. They're disjoint, they're not joined together, they're separate, right? You can just add the probabilities. If you add the probabilities when they're not disjoint, you wind up adding this middle piece twice, which is what we'll get into here in just a little bit. I think in the next chapter, actually. Okay. Rule number 5. Multiplication rule says that for independent events, to find the probability that both occur, we simply multiply the probabilities together. For two independent events, A and B, the probability that both A and B occur is the product of the probability of the two events. So, probability of A and B, as long as they're independent, is probability of A times probability of B. Okay. So, independent means that one doesn't affect the other. Okay. Independent and mutually exclusive are not the same thing. So keep that in mind. They're two separate things. Independent means that one doesn't affect the other. If I flip a heads, it doesn't affect the percentage that I'll get a tail on my next flip. Does that make sense? Okay. This can be extended to more than two independent events. We'll look exactly at that next chapter. We've got some further review there. Two events are called blank. They have no outcomes in common and can never happen together. Disjoint. Okay. The complement of an event A, the event that A that does not occur is denoted by A complement. Two events are called blank. Knowing one occurs does not change the probability the other occurs. Independent. I'll give you those for you. All right. What is this? Technology. Let's look at the sample spaces and whether or not things are really like it. All right. Which means, okay. So let's look at the event of tossing a coin. If we wanted to write the sample space for tossing a coin, it would simply be, you could get a heads or a tails in those fancy looking brackets that you don't have to really be good at drawing. Okay? Okay. If it's a fair coin, is it equally likely you get a heads or tails?
Yes.
Easy enough? let's roll a dice. We'll say it's a 6-sided die. That means I can get a 1, 2, 3, 4, 5, or 6. Assuming it's a fair dice, is it equally likely? Yes. Everybody kind of seeing how the sample space works? It's not meant to be hard. You just got to list all your possible options. Okay. Let's roll 2 dice and record the sum. So I'm rolling 2 and then adding the 2 numbers I get together. What should I start with? 2, right? I don't start with 1 because there's no way I can get a 1 with 2 dice. Makes sense. The smallest number I can get with 2 dice is a 1 and a 1, which add up to 2. Right, that goes all the way up to 12. Okay. Are those equally likely?
No.
No. Why not?
Because the probability to get 2 compared to getting 7 is completely different, because you can get 2 and a 5, you can get 3 and a 4, you can get 6 and a 1.
But the only way to get 2 is
1 and 1.
right. So you have several opportunities to get some of these middle numbers, but the only way to get a 2 is a 1 and a 1. You can get a 6 several different ways. Like he said, you can get a 5 and a 1, you can get a 2 and a 3, you can get a 3 and a 2. You can only get 12 one way, a 6 and a 6. But you can get 11 a couple different ways. So it's more likely to get some of these middle numbers than it is the numbers on the edges, right? So is it equally likely? No, it's not. True false question. Sample space. I'll just say true or false. T and F. You write true, false after that. Okay. Is it going to be equally likely?
Yeah.
I'm going to say no. Depends on the question. Right? So if I come in here, I say, is it true that all of y'all are over the age of 15?
Yeah.
Should I expect to get an equally likely answer there? Probably not, right? Because most of y'all, unless somebody's over there hiding and looks really older than they are, I think all of y'all are over 15, right? So equally likely, probably not. Okay? Now let's toss 2 coins. Sample space is going to look like heads, 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 tails, tails, heads, and then tails, tails. Now, if you write your different, you start with tails instead of heads, I don't care. I just care to get all of them, right? Are those equally likely?
Yes.
Depends.
Well,
if the order matters, yes, right? If the order doesn't matter, then that's technically the same thing, right? So I always write both. I say, yes, if order matters. No, if order doesn't. Okay. Now, I got myself a 6-sided die, and I've got a coin, heads and tails coin. Now I want to roll the dice and flip the coins, and I want to know all of my outcomes here. So I could get, I'm going to start with 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6, that's 5, not 3, 6 and a head. Then I got to go to my tails. I could wind up with a 1 and a tail, 2 and a tail, 3 and a tail, 4 and a tail, 5 and a tail, and a 6 and a tail, right? So those are my options right there. I have about 12 outcomes. Are those equally likely?
yes.
Should be, yeah, right? Because none of them are going to occur more than one time in any given order. So, yes, as long as everything's fair and the coins are fair and the die is fair, it should be okay. Now, let's toss 3 coins. Let's see what we'll wind up with. I know I'm going to have a heads, heads, heads. There's heads, heads, tails. Heads, tails, heads. Heads, tails, tails. Tails, tails, tails. Heads, tails, heads. Tails, heads, tails. Now you got 1, 2, 3, 4, 5, 6, 7. Which one am I missing? Tails, heads, heads.
Yeah.
So we've got 8 outcomes there. Okay. This one should be really similar to tossing 2 coins, right? If the order matters, then they're equally likely. If the order doesn't matter, they're not equally likely, right? If the order doesn't matter, or it does not matter, there's only one way to get this, but if order doesn't matter, this is the same thing as this, is the same thing as that, right? So, same statement. Let's put the order. Otherwise. Okay. Alright, so we've done the sample spaces. So y'all should be able to create some sample spaces if I ask you to. Let's look at finding the complement of the event, because the complement's pretty important as well. So let's look at rolling a die and getting a 6. What's the complement of that event? Remember, complement means opposite, basically. So if I'm rolling a die and I get a 6, what's the opposite of getting 6? Getting a what? 1, 2, 3, 4, 5, right? So let's put that. Easy enough. Okay. All right. Selecting a letter of the alphabet and getting a vowel. What's the complement of that? So what's the opposite of getting a vowel? A consonant. Now spell that for me.
and something to
Something like that.
Yeah.
All right. Let's select a month and get a month that contains R. So contains R in the spelling. What's the complement of that? What months we got? Not January, not February, not March, not April. Go May, June, July, about August. September doesn't work, October, November, December, so that's it, right? Yeah. What can you not purchase from your local seafood place in May, June, July, and August? It's been like 3 semesters since May. You can't get oysters in months that don't have R. Random tidbit of knowledge there for you, not on the test. Huh?
You should put it as a bonus.
I should put it as a bonus. You'll still forget by then. I'll still should put it as a bonus. I'll put it on the final, make it really. Let's select the day of the week and getting the weekend. So the opposite of that is weekdays. So say Monday, Tuesday, Wednesday, Thursday, Friday. Okay. Rolling a die and getting a number greater than 3. So what outcomes I can get that are the top? 1, 2, and 3, right? Because the number's greater than 3. That means the opposite of getting greater than 3 means I could actually do it. That's pretty simple, right? All right, next example. We got a cooler of beer because it's tailgate season. And it contains 18 Bud Light, 24 PBR, 6 Yuengling, and 24 waters. You draw a drink out randomly. Let's find the probability that we draw out a Bud Light. So, how many of those do I have?
You got 40.
Right?
So 18 out of 48.
So, how many do I have total?
48.
18 plus 24 plus 6 plus 24.
Oh, 72.
72, there it is. Okay, I'll bring my calculator out. And we'll find the actual percentage for a few of these. Just so you can see it done. Fairly looks like you can handle it anyway, but so we wound up with what? Something over 72 or
18 over
18 over
72.
72, is that right?
Yeah.
So it should give you 25%. Alright. Probability of getting a PBR. There's 24 of those. We got 72 total possible we can grab. So probability of grabbing one of those, 24 divided by 72, about 33.3%. Right? Probability of grabbing Yuengling, 6 out of 72. 6 out of 72, I think is 8.3%, but I'm not sure. Yep, 8.3%. About a water. I got 24 of those, right? I've already done that math, so that's going to at 33.3%. Everybody good so far? Not losing anybody? What's the probability we don't get a water?
48 over 72.
Yep, so it'd be 48 over 72. Which should give you what, 67 points, or 66.7%?
Yes.
Right. Now with that one, you could use your complement rule. You could say, okay, that's the same thing as 1 minus 0.333 or 100 minus 33%, because it's the opposite of getting water, right? And you can still get that same 66.7%. Now let's look at F. What's the probability of rolling a Bud Light or water? So we got to add the 18 for the Bud Light, and we also have to add the 24 for the water, right? 72. So we wind up with what?
42 over 72.
42 over 72, which gives us a percent of
58.3.
8.3%. Easy enough? Huh. Next example. A family has 3 Boston Terriers. We're interested in the gender of the Boston Terriers. Let's give the sample space of this event. Okay? So, we got 3 of them. Okay. Now I'm going to assume with these dogs, right, we got 3 of them. I'm going to assume that the order matters, right? If I set all 3 of them in a row, and I'm trying to figure out the gender, right? This one can't be, if this one's a male, I can't, the order matters, right? If this one's male, I can't make him be a female, that kind of thing, right? So in this one, the order is going to matter. I hope that kind of made a little bit of sense. So if the first one's a male, the second one's a male, and the third one's a male, I have 3 males. I could have male, male, female. I could have male, female, female. I could have male, female, male. I could have all 3 females. I could have female, female, male, female, male, female, and
Female, male, male.
female, male, male. So, like I said, this isn't the same as this, obviously, because if this one's Sam, and this one's Sam, and this one's Simon, and this one's Simon, Simon being a male as compared to a female is a completely different scenario. Does that make sense? Right. What's the probability that exactly one is a female? So I'll go through here. 1, 2, 3. Let's say I have 3 out of 8. Make sense? So the key for this is finding your sample space so you know how many options you have. Does that make sense? If you can't find your right sample space, and you only wind up with 4 out of there, you're going to wind up with the wrong percent. What's the probability exactly 2 wrong? I come through here, I got 1 here, 2 here, 3 here, also have 3 out of 8. Make sense? Not hard, actually not. What's the probability that none are female? If none are female, then they all have to be male. So I only have 1. What's the probability that at least 1 is a female? Okay, at least 1 means that 1 could be, 2 could be, or all 3, right? So if I'm looking at it, 1, 2, 3, 4, 5, 6, 7. Does that make sense? What's the opposite of at least 1 being female? None being female, right? If none are female, they're all male. Does that make sense? So I can use my complement rule there and say, okay, opposite of that is them being male, which is 1/8. So I need to choose 7 of it. And we'll do an example on the board, but that'll make a little bit more sense once it's written out. What assumptions did we have to make to complete the previous example? As I said from the beginning, we had to assume that order mattered. Order mattered, not order. others. Anything else we had to assume? We had to assume that the gender of one dog doesn't affect the gender of another dog, right? So you're like, okay, but this dog turns out to be a male, how can it really affect that other dog being a female? Let's look at it. If a family has 3 Boston Terriers and they're breeders, right? What's the likelihood they're only going to have all males or all females if they're breeding dogs? Yeah, no, you're not going to be able to breed dogs if you have all males and all females, right? Does that make sense? So the gender, if you had 2 males and you were looking for another dog to round out your 3, if you had 2 males, you were probably going to buy a female. Does that make sense? So that would affect the outcome there, right? So you have to assume, that maybe that's not what they're doing and they're all equally likely to have those combinations. You're not going to get very far as a breeder with 3 male dogs or 3 female dogs, unless you're like, I guess, leasing them out or have some kind of exchange going on or something. All right, let's look at this next example. Suppose that during the month of July in the Piggly Wiggly grocery store in Denmark, 50% of the fresh produce comes from South Carolina, 30% from other states in the U.S., and 20% from Mexico. If produce is selected at random, find the probability that the one produce item that we pick is not grown in the USA. Okay. Well, what's the probability it's not grown in the U.S.? If it's not grown in the U.S., it has to be grown where? In this example, Mexico, right? Likelihood that happens is 20%. Just got to use a little bit of logic, right? That the one produce item is from a state other than South Carolina or from Mexico. So it could be from other states, which happens 30% of the time, or it could be from Mexico, which happens 20% of the time. So 30 plus 20 equals 50%. Enough. 2 produce items in a row are from South Carolina. Okay. The probability the first produce item is from South Carolina is what? 50. Probability the second one's from South Carolina is still 50, right? Does that make sense?
Yeah.
So 0.5 times 0.5 is
125.
which is 25% of the time. Does that make sense? So you got to do it step by step. If you're picking multiple items, you have to find the probability of getting the one on the first try, the one on the second try, the one on the third try, how many tries you got. Let's follow up with D. 3 produce items in a row are picked, and none are from Mexico. Well, what's the probability the first one's not from Mexico? 80%, right? Because it could be from South Carolina or another U.S. state. So 50 plus 30 is 80. Probably the second one's not from Mexico, still 80%, right? And the third one, still 80%. 0.8 times 0.8 times 0.8, that should give me what? 0.512?
Yes.
I've done this too many times.
Okay.
So that'd be 51.2%. Okay. Let's look at E. E says at least one of 3 produce items chosen are from South Carolina. And the reason I'm going to the board is I'm going to write this thing down here, be a little more interactive. So probability at least one in the good old South Carolina. Now, there's 2 ways of doing this, one really, really hard way and one really, really easy way. Okay? The really, really hard way would mean I would have to look at all combinations. Okay? So if I'm looking at all combinations, I have to look at the combination where it's the probability the first one's from South Carolina, the next 2 aren't. The first one's not from South Carolina, the next one is. But on top of that, if I'm looking at that, I could choose the first one's from South Carolina, the first one's from another state, and this one's from Mexico. But I also have to look at that combination, and then I have to look at, and then I have to look at 3, and then I have to go back and I have to change the order here. I have to say, okay, that one, I've got to go do this one, and then I've got to be able to do, and I have to do all these combinations I can come up with, right? And then I got to make sure I don't miss any. That's really, really hard. I would suggest doing it that way. And you got to find the probability of all those different outcomes, right? what I suggest doing is using your complement rule. Complement rule says 1 minus the complement of this will give you the percent for that. What's the opposite of at least one from South Carolina? None from South Carolina, right? That make sense? Probability that none are from South Carolina. Okay, I'm choosing 3. Probability that it's not from South Carolina is 20 plus 30%, which is 50%, right? Probability the first one's not from South Carolina is 50%. Probability the second one's not from South Carolina is 50%. Probability the third one's not from South Carolina is 50%. Okay? So what I'm really looking at here, I'll factor that here, 1 minus 0.5 to the third, which gives me 87.5%. Everybody see how we use the complement rule? It's there to save you a lot of work. That's what it's there for. Everybody good on it? Okay. Next example says a certain bowler can bowl a strike 70% of the time. If the bowls are independent, what is the probability that she goes 3 frames without a strike? That means on her first frame she has to go without a strike. The chance of that happening is what?
30%.
30%. Probably happens on the next one.
30%.
And the next one.
30%.
I just need to do 0.3 to the third or multiply it 3 times. I like using exponents to me, it's easy to type in. You don't, that's fine. That is the same as 2.7%. With that one, pretty simple. Makes her first strike on her third frame. So what series of events has to happen for this to occur? Okay. She makes her first strike on her third frame. She had to miss on her first strike, right? Her first frame, right? Then she had to miss on her second frame. And then she had to make it on her third frame. You see where the percents come from? So you have to follow your series of events. What's happening here? She's making her first strike on her third frame. That means she had to miss twice and then make it. Now I just have to multiply all of it. 0.3, 0.3, 0.7. Should give me about 6.3%. Okay? Has at least 1 strike in the first 3 frames. If you see the word at least, you might need to go to complement rule. Does that make sense? Go ahead and take it. You see the word at least, you should probably think about using your complement rule. This one on board. This one's probability of at least. Was it 1 strike, 3 frames. I'm going to abbreviate it out. What's the opposite of 1 strike on 3 frames? Or at least 1 strike on 3
Not
frames.
getting any.
Yeah, not getting any, right? So that'd be 1 minus the probability, no strikes, 3 frames. Okay. Probably she doesn't get a strike on 3 frames. 0.3, 0.3, that's 0.3, right? Which should give you, what is it, 97.3%. Does that make sense? You just really got to take it step by step and go through what's going on. D says bowl a perfect game, which is 12 consecutive strikes. So that means she has to bowl a strike, chance of that is 0.7. She has to do it 12 times. I'm just going to raise it to an exponent of 12 instead of writing 0.7 12 times. Does that make sense? It has to happen 12 times. Go to your calculator, 0.7 up 12. We're looking at about 1.4% of the time. Approximately. Everybody okay with finding those percents so far? Okay. This example, it says, in a sample of 100 people, 45 had type O blood, 40 had type A blood, 11 had type B blood, and 4 had type AB blood. set up a frequency distribution and find the following probabilities. Okay. So, probability a person has type O blood. Well, how many people have type O blood in our sample? 45. There's 100 of them total, so I'm going to divide by 100. So I'll wind up with about 45%. Actually, exactly 45%. Does that make sense? Person has type A or type B blood. So type A, which is 40, or type B, which is 11. So what do I do to them? Just add them, right? So it's 51. 40 plus 11, all over 100, 51 over 100, which is the same as 51%. Okay. Person does not have type AB blood. Well, how many have type AB blood? That don't have type AB blood, how many we got left? 26. Easy enough, right? Okay. So this one uses the same percent as the one above. So what I'm going to do to kind of help us out is write these percents so I don't forget them. Help me out at least. So probability of the percent of people that have O was 45. A is 40. 11 is B. And 4 is 80. Now this next example, we're going to use the frequencies, which means the percents from above. So it's going to be 45%, 40%, 11%, and 4%. But we're not picking from the 100 people. Okay? We're sitting on our little Shepherd Bluff vehicle outside, and we're waiting for random people to show up. Our experiment showed that we should expect about 45% to be O, 40% to be A. We're not looking at that 100 sample anymore. Does that make sense? Okay. So we get people to come up. Among the 4 that show up, what's the probability that all of them are type O? That means that first one had to be type O. The percent chance it was 0.45. Next one had to be type O, and one after that, and all of them had to be. So we had to do it 4 times, right? 0.45 into 4. Should be about 4.1%. Easy enough. The reason I say that we're, and kind of made the clarification to only use the percents of frequencies from the first one and not the actual 100 sample size, is because if we use the 100 sample size here, the probability of the first one would be 45%, but that person is not going to be the next person in line, right? He's not going to give 4 times, he's only going to give once. And if we were only using 100 people, we'd have to step down. So, okay, first one was 45, the second one would only be 44, because we've already used one. Does that make sense? That's why I made the distinction and said this is not that 100 group. This is a whole separate, anybody could show up. We're just using those relative percentages. No one is type AB. Okay, AB is 4, right? Still got 4 people showing up. That means probability no one is type AB happens 96% of the time. I've got 4 people that I have to account for, so I'm going to raise it to 4. Or multiply it 4 times, right? 0.96 to the 4th. Should give you about 84.9%. We look at C. C says they are not all type A. So, if you see the words not all, you should think complement rule. Okay. So right now we see at least we think complement rule, we see not all, we think complement rule. What's the opposite of not all A?
All type A.
All A, yep. So the probability that all A. If they're not all A, then 1 could be A, 2 could be A, 3 could be A, and all other combinations of A, B, O, and whatever else is up there. So, what we're looking at here, probability that all A happens 40% of the time. I've got 4 people showing up, so I need to raise it to 4. Does that make sense? So, if I look at that, I've got 1 minus 0.4 raised to 4. Should give me 97.44%. At at least one person has type B, or one person is type B. If I see the words at least, it means my complement rule. Opposite of at least one person would be none, right? Okay. Probability that none are type B is what? So it would be, if the B's are 11%, they're not B, that's going to be 89%, right? So 0.89, and we'll raise that to the fourth because we've got 4 people coming to give blood. We've got 1 minus 0.89 which gives us 37.3 approximately. Okay with that? Let's look at this example. It says, suppose that 46% of families living in a certain county own a computer and 18% own an HD TV. The addition rule might suggest that 64% of families own either a computer or an HD TV. What is wrong with that reasoning? So anybody want to take a stab at it? Let's go.
They're not necessarily independent.
Yeah, they're not independent. Right? So somebody, they're not necessarily disjoint. Disjoint means you can have both of them, right? This is legal. You can, as America, you can own an HDTV and a computer, right? So, what you got here is some families could own both. Okay. So if 15%, I'm just kind of extrapolating there, 15% own both, you wind up adding that 15% twice. Does that make sense? You added it once with the 18% and another with the 46. You see how that works? So what we'll do next time is figure out how to deal when you have some in common. They're not just one. So you need to write that, not just one. Or mutually exclusive. You write that down better. All right. Like I said, I'll have the quiz ready by Tuesday for sure. It's just taking me a long time because I got to read through everybody's explanations. We'll finish, I think, the next chapter on Tuesday. We should have a quiz next Thursday, and I'll tell you exactly how that's going to go on Tuesday. So that quiz will be on this 12, 11, 13, and 14.